Okay, so in the previous module, we talked about the spherical polar coordinates and the Schrodinger wave equation is spherical polar coordinates for the rigid rotor, where the distance between the two masses is equal to 1, r we have taken 1, and then we said that the Schrodinger wave equation has only two variables, theta and phi. This equation we talked about. And then in this module we will start with the separation of variables. Okay. So I said you that the basic premise for the separation of variable is that if you have two variables, a wave function which is dependent on more than one variable, then you split that wave function into two component wave functions, each depending on only one variable. So this is what we did. We have a wave function psi which is dependent on theta and phi. So you split this wave function theta, capital theta depending on theta only and capital phi depending on phi only. And the total wave function is the product of the component wave functions. Here the component wave function is capital theta and capital phi. Okay. So once you write this equation, then you just place this this particular equation, put this value into the Schrodinger wave equation for rigid rotor. 1 by sin theta del by del theta sin theta. This was there. Here we were having del by del psi by del theta. So instead of psi, we write theta theta and phi phi. Here again 1 by sin square theta del square by del phi square. Here it was psi. So again it is theta theta and phi phi. Here also it was psi. So the replacement is here. The replacement is here. The replacement is here. That's all. Okay. Then we say that since we are differentiating with respect to theta, so phi part will be a constant. So bring this phi part outside and it will be phi phi divided by sin theta del by del theta sin theta del theta theta divided by theta. And then here we are differentiating with phi. So theta theta part will be constant. So bring theta theta part outside, then it will be sin square theta and then del square phi phi divided by del phi square, and this will be this will remain same. Then we say that you divide by theta theta and phi phi. So that you have 1 by theta theta sin theta divided. If you divide phi phi will go here and theta will come in the denominator. So theta theta sin theta del by del theta sin theta del theta theta by del theta. You look at this equation, 1 by theta theta sin theta del by del theta sin theta del theta theta by del theta. So in this part you have only theta only. You do not have phi. Then you look at this equation. You have 1 by phi phi sin square theta del square phi phi del phi square, but in this equation you have theta also and phi also. So the separation is still not complete, and if you divide it by theta theta and phi, this will go and you will have 8 pi square I e divided by h square. Then what you do? You divide this, multiply this equation by sin square theta, and this will result into sin theta. If you multiply by sin square theta, then this sin square theta will go, because if you are multiplying by sin square theta, this sin square theta will go. So what will happen? You will have sin theta, because here also in the denominator there was sin theta, so you are multiplying by sin square theta will become sin theta theta theta, and now we have this part where theta only, this part where phi only, and this part where theta is present. So these two part 1 and 3 is theta dependent and second one is only phi dependent. So we club these together, 1 and 3, here we have clubbed, and this is from theta dependent only, and the second one is phi dependent only. Okay. So what we can write? We can write, you bring this phi phi part on the right hand side and then it becomes minus 1 by phi phi del square phi phi by del phi square. Okay. Now both these equations LHS and RHS are equal to a constant. Then only it will be a valid equation. Okay. So we equate it to a constant, and that constant is m square. And if you put m square, then you can put LHS equal to m square and RHS also equal to m square. And if you do this, then the first equation which you write is del square phi phi by del phi square m square. Okay. You see, what this is equal to m square. Okay. and bring this on this side, it will be positive value, and multiply by phi phi. This how do you get? You get it 1 minus 1 over phi phi del square phi phi by del phi square is equal to m square. So what you do? I bring it, I make it 0, m square plus 1 over phi phi del square phi phi by del phi square I can write. Then multiply whole equation by phi phi. Multiply by phi phi. So this LHS will remain 0. This phi phi multiplication will give you m square phi phi plus this phi, you are multiplying with phi phi, so this will go and you will have del square phi phi divided by del phi square, and this is actually this one. Okay, del square phi phi by del phi square plus m square phi phi is equal to 0. Okay, this is your phi dependent equation. Phi dependent, only one variable, phi dependent equation. Okay, then in the next case, this equation is again equal to m square. Okay, so this equation again, now for simplification we divide it by sin square theta and multiply by theta theta, so that what you get is 1 by sin theta. If you divide by sin square theta, then this sin theta will come here, d by d theta sin theta del theta theta by del theta plus 8 pi square I e divided by h square. You are dividing by sin square theta, so this will go, and you are multiplying by theta theta, so this will come. So theta theta divided by sin square theta, and this we can write. If we take 8 pi square I e by h square as beta, then we can write this equation. So this is the same equation, beta minus m. This if you bring this on this side, RHS side, from RHS to LHS, this will become negative. So m square sin square theta, theta theta will remain here, and beta theta will be here. Okay, so it will be theta dependent equation. So these two equations, equation number 1 and equation number 2, are equations which is dependent on only one variable. Equation number 1 is phi dependent equation, and equation number 2 is theta dependent equation. Okay, so once we have got these equations, now we separately we will try to solve these equations, theta theta and phi equations and theta equations. And simply by appearance you can see that the easier equation is to solve is phi equation. Okay, and this you have already done, so let's play with the phi equations. This equation, if you look very closely, you are already aware of an equation, d square psi by dx square plus kx square is equal to 0. Okay, let me do it like this one. D square psi by dx square plus 8 pi square m e by h square, 8 pi square m by h square e psi is equal to 0. This you take k square. Okay, you remember this? This was the equation for particle in a one-dimensional box. Okay, compare this with this equation. Instead of psi, you have phi. Instead of x variable, you have phi variable. Instead of k square, you have m square. So the solution is known to you. Okay, this solution is known to you. It's not something new equations. Okay, and we can write the exponential solution for this one, and the exponential solution could be phi phi is equal to exponential plus minus I m phi. This is the solution. If you want to prove this, then in the usual way, what you do, you differentiate this equation, this psi value or wave function value once and then again twice. So the first differential will give you plus minus I m exponential plus minus I m phi, and if you do the second differential, it will be plus minus I m square exponential plus minus I m phi plus this is equal to plus I square m square exponential plus minus I m phi, and this you can write as minus m square phi and minus m square phi means again equivalent to equation number 1. So, one of the solutions, certainly one of the solution of this equation, phi equation is phi is equal to exponential plus minus Im phi. Very easy. Then what is this solution means? What is the boundary condition for this solution? Now you see for the boundary condition the variable is your phi. Okay. In case of particle in a one dimensional box, you write the solution a sin kx plus b cos kx, and you say at x is equal to 0, psi is equal to 0, and at x is equal to a, psi is equal to 0. These are the boundary condition. So, with respect to the variable, you write the boundary condition, and here the variable is phi. And what is the value of phi? I said you in spherical polar coordinates, phi varies from 0 to 2 pi. Phi is 0 when you drop a perpendicular on the x-axis. Your particle is exactly on top of the x-axis. Okay, and you drop a perpendicular and it falls on the x-axis, then the line joining this perpendicular and the origin will be on the x-axis, and it will form a 0 angle. Okay, and since it is an angle, it is an angle in the plane. So, starting from this, if it completes one rotation, the angle which is covered is 2 pi, and again after 2 pi you reach at the same point on the x-axis. 2 pi rotation again gives you the same x-axis. Okay, after 2 pi rotation. So, the boundary condition for this particular equation is that at phi is equal to 0, the equation is this equation will be equal to 1, and phi is equal to 2 pi. The equation tells you that it's exponential plus minus Im 2 pi, and the boundary condition tells you that phi is equal to 0 and phi is equal to 2 pi is the same point x-axis, because phi is equal to 0 you get when you are on the x-axis, and phi is equal to 2 pi you get when after one complete rotation you come back on the x-axis. So, whether you say phi is equal to 0 or whether you say phi is equal to 2 pi, in a space you are at the same point on the x-axis. So, the value of the function should remain same at phi is equal to 0 and phi is equal to 2 pi. Whatever the mathematical equation you get for phi is equal to 0 and phi is equal to 2 pi must have the same value. This is what is the boundary condition for the phi equation of rigid rotor. So, phi is equal to 0 and phi is equal to 0 and phi is equal to 2 pi is equal. Okay. Or you can say if it is not 0, if it is 10 degree or 20 degree, phi is equal to 20 degree, then again after one complete rotation of 360 you again come back to the same point. So, phi is equal to 10 degree plus 2 pi. Okay, this rotation will give you. So, you say phi is equal to phi plus 2 pi. This is the boundary condition. So, boundary condition in rigid rotor for the phi angle is that phi wave function, capital phi wave is a wave function value at phi is equal to wave function value at phi plus 2 pi. If phi is equal to 0, then phi you can write this one, phi is equal to 0 is equal to phi is equal to 2 pi. Okay, both are the same thing. And at phi is equal to 0, you have written function to be equal to 1, and phi is equal to 2 pi, the function you have written plus minus Im 2 pi. Okay. So, what do you mean to say? You mean to say 1 becomes equal to exponential plus minus Im 2 pi. Okay. This exponential equation can be converted into cosine and sine functions, okay, which tells you that if you put m is equal to 0 value, then this becomes equal to cos 0 1, and this becomes equal to sin 0 0. So, it becomes equal to 1. Same way, when you put m is equal to plus minus 1, then also the e to the power plus minus Im 2 pi becomes equal to 1. When you put m is equal to plus minus 2, then also it becomes equal to 1. What does it mean? That this boundary condition restricts the value of m to 0, plus minus 1, plus minus 2, plus minus 3. Remember this, the same boundary, when we applied the boundary condition particularly in a one dimensional box, what did we get? we get quantization. Here also you say that m can have a value 0, plus 1, minus 1, plus 2, minus 2, plus 3, minus 3, nothing else. And this is again a quantization, because you are restricting the value of m to a particular value. It cannot go indefinitely or in any manner. Okay. So, the boundary condition is very important in quantum mechanics. Boundary condition is the basis, is the reason for all kinds of quantization which appears into the problem, okay, into the system. So, therefore, m has a limited value of 0, plus minus 1, plus minus 2, plus 3, plus minus 3. And if you have this value, then you can write the different wave functions, because phi value we have written as exponential plus minus im phi. So, if phi is equal to 0, what is the value of the function? If phi is equal to plus 1, what is the value of function? If phi is equal to minus 1, what is the value of function? This you can write. And see, so these are the different phi functions. Phi is equal to 0, exponential 0, phi is equal to plus 1 e to the power I phi, phi is equal to minus 1 e to the power minus I phi, phi is equal to plus 2, and so on. You keep on writing for 3 and so on, you can write. Now, the next thing is that once you have the wave function, the next task is to normalize that wave function. Okay. So, this normalization of wave function again is we do everywhere, because normalized wave function facilitates in calculating the physical quantity values for or expectation values of many different quantities. And by normalization, you try to contain your system within the boundary. That's the most important thing, because if your system is not within the boundary, you cannot play with the wave functions. So, the second task is the normalization of the wave function, as we have done earlier also. So, here also we will do the normalization, and this normalization is also very easy, because normalization condition remains same, psi star psi d tau is equal to 1. Okay. Here we have only the phi part of the equation. So, the volume element is d phi only. I said you earlier that in case of spherical polar coordinates, the volume element involves dr also, d theta also, and r also. Okay. But here we have separated the equations into different components, and this component contains only one function, only one variable phi. So, the volume element is d phi, and the limit of this phi is from 0 to 2 pi. I am saying you time and again, because this is something which should be in your brain at every point. Okay. So, phi varies from 0 to 2 pi. So, minus infinity value is 0, plus infinity value is 2 pi. Okay. N is the normalization constant. So, n e to the power im phi, and then again complex conjugate. So, minus im phi. Okay. And this is again normalization constant. The two, this is one function, this is another function, normalized function, then d phi is equal to 1. And so, it becomes e to the power 0 d phi is equal to 1, and e to the power 0 is equal to 1. So, it is d phi, integral of d phi between limit 0 to 2 pi, and the normalization constant comes out to be 1 by root 2 pi. Okay. If you add this, then this normalization constant will be same, and you can write the different phi functions with this normalization constant. So, for phi is equal to 0, you do not have anything except normalization constant, because exponential I phi 0 becomes equal to 1. So, this is the phi 0, the phi plus 1 is e to the power I phi, phi minus 1 is e to the power minus phi, and everywhere the normalization constant is 1 by root under 2 pi. Okay. So, all these functions you can write, but this function has imaginary part I. So, sometime interpreting this function becomes difficult, and we have the de Moivre's theorem with which you can convert this into trigonometric functions. So, with the trigonometric functions also, I have written the equation phi is equal to 0, phi plus 1, phi minus 1, phi plus 2, and phi minus 2. Okay. This we did earlier also in one case, and we will be doing again. So, and you will come to know that how do we convert this imaginary function into real functions with a trigonometric function like cos phi and sin phi. Okay. So, few normalized wave functions of the phi equation are this one. And the remarkable thing is this, that in all these equations you have phi as the variable except phi is equal to 0. Okay, at when the phi m value is 0, these are m values. M I said you could be 0, could be plus minus 1, could be plus minus 2. So all this what we have written is phi m values, phi m values. Okay, and this phi is the same phi which you are aware of from your +2 standard called magnetic quantum number. You were knowing that if L is equal to 1, azimuthal quantum number is equal to 1, the m could have 3 different values, 0, plus 1 and minus 1. Okay. Why plus 1 and minus 1? Why not anything else? You have seen this equation, that this tells you that why the m value is restricted to 0, plus minus 1, plus minus 2 and plus minus 3. So whatever you have learned about the quantum number, now you are going to prove it using the quantum mechanical calculations, that whatever you have learned earlier is correct or not correct. We will see. Okay. So this is actually the magnetic quantum number which we have done earlier. Okay. So we have the equations, we have the real equations also. What is the point of doing these calculations? What is the physical significance of phi? Okay, we have the phi functions. Then what is the physical part of this phi functions? Why do we do this one? Okay. Now for this, what we say, what we will, it's a little digression from the normal rigid rotor, because I want just to tell you the significance of this phi function. So what I have written is that if you have angular momentum L, then this L is a multiple of R into P. Okay, where this R could be written as, in the vector form, R and P could be written like this one, or could be written, this matrices can be written. Okay, I, J, K, X, Y, Z and P, X, P, Y, P, Z. So if you use this particular matrix, then what you can write, Y, P, Z, Z, P, Y into I, and X, P, Z, Z, P, X minus Z, P, X into J, and then X, P, Y, Y, P, X is equal to K. This is your Lz component of the total orbital angular momentum, Z component of the orbital angular momentum. Okay. And if you look at the 3-dimensional space, then this is your x coordinate, y coordinate and z coordinate. Then R and P are in the xy plane. This R and P is the shown in green. R and P is in the xy plane, and the Lz component is along the z axis. Okay. So phi corresponds to circular motion in the xy plane. We are talking about this motion. Whenever you say phi function varies. Now I have the normal in the normal representation, what you find is that this is your x axis, this is your y axis. So you can put anywhere. It could be like this also. Okay. So if it is your x axis here, then phi is equal to 0 at x axis, and again after one complete rotation you come back to phi is equal to 2 pi. So it is the same point where phi is equal to 0 also and phi is equal to 2 pi also, I said you earlier. Okay. So this phi corresponds to a motion in the xy plane, and your Lz component could be written as the operator for the Lz component of the momentum. L is perpendicular to the xy plane angular momentum, and Lz component could be written as h cross I x dy. You look at this one, x dy and y dx. And if you do certain algebra, then in Cartesian in polar coordinates, Lz becomes, z component of the angular momentum becomes h cross by I del by del phi. Okay. So we were talking about the solution of rigid rotor. We found the phi functions, and now I am going to tell you the relevance of the phi function. Okay. These are something about the angular momentum, the Lx component, Ly component, Lz component, and then these are commutators Lx and Ly, if the commutator for Lx and Ly means if you write Lx Ly minus Ly Lx, this is actually, if you remember, because we did our commutators earlier, Lx Ly commutator. Okay. Same way, Ly Lz minus Lz Ly is the commutator Ly Lz. Capital L is all capital L. Okay. Because if you remember, I talked about A and B operator minus B and A operator is actually a commutator of A and B. And commutator is shown within the bracket. So if you use this one, you look at the Lx Ly commutator, Ly Lz commutator, Lz Lx commutator, all have value equal to I h cross into Lz into Lx into Ly. Okay. And this is your total angular momentum is L square. L is the total angular momentum. L is the total angular momentum and Lx, Ly and Lz are the component angular momentum. But the commutator of L square with Lz gives you a 0 value. And this we will prove when we will talk about the angular momentum in details. Okay. What does it tells you? It tells you that if the two commuting operators L square and Z and their commutator is equal to 0, then they are simultaneously measurable. Okay. We can measure them simultaneously and precisely. Okay. So these are not the conjugate variables like position and momentum, because position and momentum operator commutator is not equal to 0 and they cannot be determined simultaneously. Okay. So what we see here is that this commutation relationship, I have just copied it to tell you that angular momentum plays a very important role. Which we will do in details about the angular momentum. But some of the commutation relationship is this one, and this is important, that this commutation relation tells you that the two L square and Lz can be determined simultaneously and precisely. If you do that, and if you use whether phi function is an eigenfunction of Lz operator, so Lz operators I have taken as Lz is equal to h cross by I del by del phi. It's exactly the same thing which we did in case of Px operator. Px was what? Minus I h cross d by dx. Okay. So Px was minus I h cross d by dx, or h cross by I d by dx. Okay, h by, and here also you have Lz is equal to h cross by I d by d phi. Okay. So if you do this, if you use this particular operator, then what you do? This is your operator, this is your function. Operate with the function, and what do you get? H cross by I d by d phi 1 by root under 2 pi e to the power I m phi. So a differential of this will be I m exponential I m phi, and now we can write m h cross 1 divided by 2 pi. So what do we mean? This is also your phi m. You get the function back when you operate with the operator Lz on phi m. You get the function back with the eigenvalue m h cross. So m h cross phi m you get, and so the z component of the angular momentum you can obtain, which is equal to m h cross. Okay. Z component of angular momentum you get, which is called m h cross. Further, since m value is limited and it is quantized, so it talks about that a specific direction of z component of the angular momentum, because m is quantized and m has 0, plus minus 1, plus minus 2 values. So if it is quantized, then it tells you the orientation of z vector, Lz vector in a space, and this also talks about, this is what is called a space quantization, and which you can say is a space quantization concept. For a rigid rotor, the angular momentum Lz can point only in certain fixed directions because m has fixed values. So, for L is equal to 2, m is equal to 0, plus minus 1, plus minus 2. And if the z component has this direction, then the rotation will be this one. If z component has this direction, then the rotation will be this one. If the z component has this direction, then the rotation will be this one. So, it is actually this is rotation in a space is changing, not only the component. With respect to z component, this rotation is z component, then this rotation is this z component is this rotation, this z component is this rotation. So, in a space, this particular and what does it mean? That all kinds of rotation is not possible. Rotation is possible in for one particular direction, second particular direction. If you have two angular two values of Lz, then only two rotation is possible, this one and this one. Okay, and if you have 5 different values, then this one also, this one also, this one also, this one also, and this one also. Look at the finger, because this is what is called a space quantization. So, if z component of the angular momentum is quantized, since m can have certain specific values, for L is equal to 2, m can have these values, and so the quantization is like this one. This is your z component, Lz component, and this is your rotation value. So, if you have a fixed values of m for L is equal to 2, all this is m actually, m, and m. M is plus 2, plus 1, 0, minus 1, minus 2. Okay. This happens for copy paste, this L remain there, you change it, it's equal to m. Okay. So, for L is equal to 2, m has 5 different values. So, the Lz orientation will be these different orientations, which is possible. And again, if the rotation is like this one, then you can draw from the originating from the center, you can draw something like this one. For this, you can draw a rotation axis space quantization like this one. So, the concept of a space quantization comes from the phi equation, and the value of eigenvalue of the Lz component of the angular momentum also you get from the phi functions. This is the physical significance of phi functions. Okay. So, the solution of phi equations and the solution of phi functions we did. We did the physical concept also, physical interpretation also. Then in the next module we will talk about the theta equations. So, what is the solution of theta equation? This we will talk about in the next module. Okay, thank you.